Hey, welcome back to discussion 23. We're looking at problem 1 on the homework, where you have a arm held perpendicular to the ground and it's holding a mass. Okay, so here is a model of the arm. There's a much better picture of it in your worksheet, but essentially we have the flexor muscle here at 0.05 meters, 5 centimeters from the elbow, and then you have the center of mass is 1 and plus, so it's 0.15 total. It's 0.15 meters, 15 centimeters from the elbow, and then you have 45 centimeters out. You're holding a mass, and now we are told that the mass is 10 kilograms. We're also told that the forearm weighs 20 newtons. So 20 newtons is your weight force, and we know that that's equal to mg. Right? So then if we want to know the mass of the arm, I'm not sure if we'll need it later, but if we want to know it just to have it ready, call this m1, this is the mass, m1, we just take 20 over 9.81 meters per second squared. Right, this is 20 newtons, and that leaves you with a value of 2.04 kilograms. So mass 2 is equal to 2.04 kilograms. That's how much mass is in the arm. Okay, so overall we're asked to find what is the tension in the flexor muscle. Okay, so let's recall in the worksheet. I should point out that in the worksheet it says that this tension force is M. I like to use F sub T to remind me that it's a tension force. Okay, so anyway, let's recall that torque is equal to R cross F is equal to R F magnitudes sine theta. And now, so let's look at all of our we have three forces here, right? We have a weight force here, we have a weight force here at the center of mass, that's what we're told. And then we also have a tension force that's pulling upwards. So let's look at this. These masses here are perpendicular to this line, which is the arm. Our arm is held perpendicular to the ground, right? So that means when we're considering this sine theta, this is the angle between R and F, right? So we have R here F here and R here. The angle between them is 90. Similarly, for this, and this, all of our angles between the F and R are 90, and that just gives us sine 90 is 1, right? So we're told that this thing is supported, which means that this arm is in equilibrium. This system is sitting in equilibrium. Nothing else is happening. The mass is supported by the arm is held perpendicular to the ground. So what that means is if we're in equilibrium, the net torque on the arm is 0. Okay? So now we sum up all of our forces, right? So this is in the opposite direction of these, so we'll obviously need some negative value. We can consider that negative if we want. So let's take this. R is 0.05 meters times Ft, right? Remember sine 90, that's going to be 1. And then we'll consider this the negative direction. Okay? Then we have, similarly, this is 0.1 meters times the weight force, which is 20. So 0.1 meters times 20 newtons, we're told. That's going to be at the center of mass. It's the only place that really makes sense, right? You're not going to have a weight force out here for the whole arm. Okay, so then we have 0.45 meters. Oops, excuse me, this value was wrong. It's so this is actually, so my diagram is a little misleading. So here, this value, according to our diagram in the worksheet, is 1 meter. And this value is 0.05 meters. Sorry. What I'm saying is this is 0.05 meters, this is 0.1 meters, right? So that means that the total value here is 0.15 meters. 0.15 meters. Okay, and then this weight force, we're told this thing is 10 kilograms. So mass times gravitational acceleration will give us our weight force. And remember, all of these were sine 90. This is torque. It's R, magnitude F times sine 90. But we know that sine 90 is 1, so I just neglected to write those down. So now we have 0.05 meters times Ft is equal to, excuse me, 0.15 times 20 newtons. Well, let's just not cut corners here. 20 newtons plus 0.45 meters times 10 times 9.81. This is going to be units of newtons. Newton meters. Okay, then we just plug this into a calculator. So we set this up. Let's do it this way. This way. And then we say 1 over 0.05 meters. And this comes out to be 942.9 newtons. So we are given a force, and then we're told whose position from the axis of rotation is given by a position vector, r, negative 5.8 I hat meters, right? And then it says find the torque. So we just take r cross F. F, right? So then we just take this cross product. Pretty much that's what we're going to do a bunch of times because there's 3 questions. There are 3 questions that are very similar all in a row. So this is negative 5.800. This is R, right? And then F is going to be down here where 65.8, and then we have 96.3. It's 0. So we take the cross product. We end up with 0, 0, 0, 0. This is a value that's 0. So then our only value is going to be 5.8 meters times 96.3 newtons. This is going to be in the k hat direction. That's your torque. That value, 558.54. This is negative, by the way, k hat. So that's your torque. Part B says, what happens to your answer if the force's x component increases while the y component remains constant? So if the force's x component increases, so if this thing increases, that's a dark color, let's use something bright, right? If this thing increases, what changes? Well, this is still 0, this is still 0, so then we still only have values in the k hat direction. This value here is going to stay the same, so this is the same. If this increases, nothing changes because we don't have anything to cross in the j direction. So nothing changes. So part B, no change. Right? Part C, what happens if the force's y component increases while the x component remains constant? Well, if this increases, then this value is going to increase as well in the negative k hat direction. So what does that mean? It means it's going to be larger. So that means that the torque will be larger. I guess we'll just say will increase. in the negative k hat direction. And then number 18 is very similar. We are given the exact same force. I'll just take this. Oh, I forgot to write down the k hat. Excuse me, I hat was here. So anyway, I'm going to take these, copy them, bring them down. The force is exactly the same now, but the position vector is in the k hat direction. So again, we can just take all of this, copy this stuff, because it's the same except for one change, and that change is going to be that now our position vector is in the k hat direction. So then it says find the torque, right? And we got to do that. I hat, this is 0, this is not 0. So we have 0 minus negative 5.8 times 96.3. This is I hat. And then what do we have for j hat? 0, not 0. So we have minus, excuse me, minus 0, right? For j hat, this is 0. This is non-zero. Minus negative 5.8 times 65.8. This is j hat direction. And then in k hat direction, we have 0, 0. So nothing in the k hat direction. Just write that out. Why not? So for the I hat direction, we're going to have a positive value, right? I hat, negative, negative. Positive value of the same thing we had before. It was 588.54. I hat minus. I'm just checking to make sure I have this. Yep. Okay. And then so now we have, well, this is negative, that's positive. This is another negative, that's going to be negative. This gives you a negative value of 381.6 newtons j hat. So this is your force, or sorry, this is your torque, Newton meters. And that's what we have. So now it asks again, what happens if x component increases and y is constant? So if this increases, then what happens? Well, the I component is not going to change for the torque, but the j component will change for the torque. This is going to increase in the negative j hat direction. So torque increases in negative j hat direction. That's what changes. Okay, part C. Similar question. What happens if y component increases and x remains constant? So if the y component increases, what changes? Well, where is this? Not here. J component is going to stay the same, and I component is going to increase in the I hat direction. So we say that torque increases in I hat direction. So hopefully that's clear. Pretty much all we're saying is if this component has a higher value, it doesn't really affect this because it's not, this value isn't sitting here, but it does affect this component because this value is right here, right? So if this increases, this overall value also increases. Next, part number 19, part of the same series of questions. All right, so I'm just going to take, it's very similar, so I'm just going to steal all of this and change a couple of things. Now I think our components change. I think our directions actually change. So let's see what we have. I hat, k hat. So this is in the I hat, this is in the k hat direction. And then, oh, this one we're actually given a torque. So we're actually given a torque. We're told that the torque is equal to 57.1 newtons in the j hat direction. And then it says find RZ in the k hat direction. So what we have to do here is, well, what I want to do is I just want to set up a cross product like I normally would, right? Just to kind of show what's going on here. So torque is equal to R cross F, right? That means that we're going to have I, J, K. We have R, Z component, and then nothing here. And then we have I and K components for F, right? So this is going to be I component and K component. All right, and then we take the cross product to see what happens. So in the I hat direction, this is 0, this is 0. In the J hat direction, this is 0, this is non-zero, so this is what we're going to get. So we had a 0 for the I hat minus the J hat direction. The first one was 0 minus. I should be more explicit just so that I'm not confusing anyone. 0 minus 0 I hat minus 0 minus, right? Because this was 0 minus 0. Now we're on J. 0 minus this value. RZ F sub x. So the x component. Okay? Now we take this. What is in the k direction? 0 minus 0. K hat. Okay, so those go away. We're left with what? We're left with negative of this negative value here. So we have RZ times F, x component of F. Okay, this means that, remember, we're told that torque is 57.1 in the j hat direction. See, torque, right? 57.1 Newton meters in the j hat direction. This is also in the j hat direction, so we're actually doing really well. Oops, j hat direction overall. And then we take RZ, the thing we're solving for, times the x component value, which is 65.8 newtons. And then we just solve for RZ. So RZ is equal to 57.1 Newton meters over 65.8 newtons. Gives us some value in meters, which is 0.8677 meters in the k hat direction, or let's just call it, I mean, you could just call it 1 if we're really rounding. Just call it 0.87 meters k hat. Next problems are 20 and 21 on page 412. Before I change the page, I should note that I was only writing down the magnitudes here, so the vectors are not relevant, but they would be. The final answer is R is equal to, right, this is what we were asked to find, right? So this is RZ. So the final answer is 0.87 meters k hat. That's what you're asked to find. Alright, now we can move on. So we're given that a man is holding a dumbbell and his arm is bent. So now we no longer have this perpendicular situation. We have a bent arm. And we're told that the torque exerted by the dumbbell around his elbow is 38.9 Newton meters. So that looks something like this, where this is the bicep, this is the elbow, and then this is the dumbbell that he's holding. We want to figure out what the mass of the dumbbell is. And we can do that by setting up a torque equation. We're told what the torque is. So here, excuse me. So here we have a recall that this is the relationship, of course, and then we have this. At this point, we should all be tired of seeing this, but that would be a good thing, because that means you're learning it, right? So let's see. So we are told that torque is 38.9 Newton meters. Newton meters, right? We know, and we're trying to figure out what is the torque around, or what is the mass of the dumbbell using the torque around the elbow. So this is our hinge point right here, right? So this is going to be your position vector here from, we'll call this our origin, and this is our position, which is going to be 0.325 meters. And then our force with which this position vector is crossed is the weight force of the dumbbell going this way, right? Going down. So let me draw that. Or I think I actually have a extra. Just duplicate that. Pull that up. Because I actually drew it before. So here. So now, so what I'm saying is we want to consider this position vector and this force. The angle between these two things, since we know that this is 42.7 degrees and this is a right angle, we can just draw perpendicular. This gives us 47.3 degrees. So that means this 0.325 meters is our R. The force is the weight force, mass times gravity, right? And then we want sine of the angle between those two things, where our angle happens to be 47.3 degrees, right? Again, because we're told in the general situation we're given this angle down here. We know this is a right angle. So we draw a perpendicular, figure out 90 minus this angle. So 90 minus 42.7 gives us 47.3 degrees. So this is going to look like 0.325. What is the mass? The mass is what we're trying to solve for. Gravitational acceleration, squared times meters. We had a meter there. And then so now it's sine of 47.3 degrees. Okay, this is our equation. So we just solve for m. So m is equal to 38.9 over all this other stuff. This is Newton meters. This is a meter. Excuse me, so these units cancel. 9.81 meters per second squared. Right, and we're hoping to end up with kilograms, right? So Newton is kilogram meters per second squared. So the second squared goes away, the meters goes away, and that leaves us with kilograms as our units. Definitely check that if you don't believe it. Okay, so what is this when we plug it into the calculator? Oh, we also need, don't forget the sine of 47.3 degrees. Right? So this gives us a value of 16.6 kilograms. So the mass of the dumbbell is 16.6 kilograms, or approximately 37 pounds. That was my dog. All right. Next problem is the same scenario. We want to know what is the torque exerted by the dumbbell around a shoulder. So this is our basic setup once again. We know that this is 90 degrees down here. We're told in the diagram that this is 47.3, so we know that this angle over here with respect to a horizontal line is going to be 42.7. So let's go ahead and draw a horizontal line, and I'll mark a couple things here. Okay. All right, so now, right, so we have this unknown position vector r. We also want the torque of the dumbbell on the shoulder. This is our hinge point now. It's here, right? This is the weight force. Okay? The angle between these two things is going to be what? This is straight horizontal, this is straight vertical. So this is going to be a 90-degree angle. So that makes our lives a little bit easier. So let's set this up, right? We want torque is equal to, again, r cross f is equal to magnitude r, magnitude f, sine theta, where theta is the angle between your vectors. This is our position vector. This is our force vector. So we have this crossed with this, right? The angle between them is 90. So this goes to 1. Right? So now we just have magnitude r, magnitude f. Well, overall, again, we're after, this is going to be torque number 2, I'll call it, because this torque up here that we found earlier was torque number 1, right? We're told that torque number 1 of this weight force around the elbow is 38.9 for the elbow, right? Newton meters. But for the shoulder, T2, we don't know what that is. We don't know what it is going around this direction. That's what we want. So we're going to need some information. What are we missing? We want T2. Sine theta has gone away. We need R, we need F. Well, F is just equal to the mass of the dumbbell, 16.6 kilograms. That's what we found, right? We found that. Oops. Times gravitational acceleration, because we're just talking about a weight force. So now, so we filled that in. Now we just need to figure out what is R, okay? So let's take our diagram here. I'm just going to copy it, and then we'll simplify things a little bit so that we can get a better view of what's going on. Okay. We want to figure out what is R, right? Actually, we know. Now, if we turn this thing like this, this is y, it's equal to 0.325 meters. This is x, it's equal to 0.3 meters, right? We know these angles. This is 47, up here is 42.7 degrees. This is 47.3 degrees. So we should be able to figure out what R is just given this information. Right? What is R? R is equal to the square root of, using the Pythagorean theorem. Since we know what these values are, we can just square those. 0.3 squared plus 0.325 squared, all under a square root. Doing that gives us a value of 0.4423 meters. That seems reasonable enough, considering that this is going to be a little bit longer than both of these, right? And it's approximately on the same order of magnitude, so I think we're doing good. So let's go over here, let's plug this in. 0.44, we'll just call it 0.44 meters, times 16.6 kilograms, times 9.81 meters per second squared. This is all going to give us units of a Newton meter. Just fixing that a little bit. And this gives us a value 72 Newton meters. That's the torque around the shoulder. That's the answer you're looking for. So this torque from this dumbbell around the shoulder at this hinge point, 72 Newton meters. Okay. Moving on to the next problem, number 79 and 80. Okay, we're given that we have a rope that's attached to a pole. Here's a pole, here's a rope. Okay, it's holding a rod, which I drew here. Now on this rod, there's a sign that has a weight force we're told is 10 newtons. Okay, so let's call this FW1 is equal to 10 newtons, because I have this marked here, mass 1, mass 2, right? FW2, we're also told, is 10 newtons. Okay, then we're told that these angles here are each 30 degrees. So I'll just write that down here. 30 degrees. 30 degrees. Right? Let's see, what else? We're told that this angle here is 45 degrees. Okay, so now what we're asked to find is the magnitude of the tension in the rope above the rod that is also attached to the wall, right? So anyway, what it's asking for is what is the magnitude of this tension force here. So we actually want this. Let's make that a little more clear. This. We can do this a few different ways, actually. But I think the easiest thing to do is just going to be to sum up our forces in component form. So we're going to have a y component of the tension force going this way. We're going to have an x component of the tension force running along this rod this way. Actually, let's just leave that there. Right? We'll draw it over here just to make it a little easier to see. FTX. So we can get rid of that. Nope, it'll be fine. We're also going to have a weight force, right? Here's the center of mass here. This thing has a weight force going straight down, FW1. Okay, we're going to need to consider that. So FW1, we'll call this here, straight down. That's in the y direction. FW2, we're going to have this thing. We can consider it here, since these are perfectly equivalently apart. I guess that's the best way I could think to say that. These are equivalent, right? So this is the center of that. This is going to be at, this is 2, and this is 1, this is 3 meters. So I would consider that weight force at 3 meters. You could also just do component form. You could have an x component and a y component. This would be FW2y, and then you would have an FW2x as well. That is another way that you could do this. Okay, but I'm just going to make it as simple as possible. I would break it down where you're just summing up the torques. So everything is in equilibrium. The sum of the torques is 0. I think this is the method that you're expected to use for this problem, because here's your magnitude of F. Here is your R position vector. This is 45. So magnitude R, magnitude F, sine 45, right? R, Ft, sine 45. Right? Which incidentally is the same as what we had written down before, right? And again, the torque here, because this is sine 90, this is going to be position vector 2 meters, r hat. And this is weight force straight down, right? So this is still going to be 2 meters times 10 newtons times sine 90, right? And then the same thing, 3 meters, 10 newtons, sine 90. Well, this gives you the exact same answer because these go away. This goes away. This is exactly what we had written down before. This is the same as what we had done before. That's method number 2. The other method that you could use, and by the way, this is the method I would recommend considering when you have a torque problem, is to really just do what is the torque rotating about this hinge, right? You're told that this is the origin. So what is that? What is this torque here? Okay. The other method is to, as I was mentioning before, you want to sum up the torques at each of these locations, right? So you'd want the torque here and you'd want the torque here. So how you would get that is take your position vector, which at this point is 4 meters out, right? Here's your magnitude. This is the magnitude of the force. Here's your angle. So this would be the force. Here's the angle, and the position vector goes all the way over here, right? So that's another way. And then you would do the same thing for the other force. So you'd go all the way here, and then this would be your position vector here. Sorry, position vector here, force here. You could just consider this angle, right? You could take the sine of this angle. That should give you the same answer. Okay, so I think I mentioned earlier that this was sine of 60, but that was wrong. It's actually sine of 30 because this is the position vector and this is the force vector. This is 60, this is 30, sine of the angle between the vectors, right? So if we just set that up real quick, this is going to be similarly ft sine 45, just like before, and then the other forces going downwards, we're going to have 2 times 10 times sine 90, right? Because this is for the this one here, position vector, force, sine of the angle between them is 90. So next we're going to go with, okay, we're going to go 2 meters out for this blue one, like I was describing earlier, 2 meters out, and then the force vector is here, sine of 150. 2 times 10 newtons, sine 150. Because that's the angle between them, right? Right, this is 30. That means this one is 60 if you draw a perpendicular. If we draw a perpendicular here, let's just draw it because you can't see it. So this is 60, this is 90, so this angle is 150. Okay, so sine of 150. Next, we're going to be using this 30 degrees, 4 meters, force, sine of 30 between them, which gives us minus 4 times 10 newtons, sine 30. So putting all this together, we get Ft is equal to sine 90 is 1, right? Sine 150 is the same as sine 30. That's actually 1/2. Sine 30 is 1/2. So now we have 20 newton meters, excuse me, plus this is what, 10 Newton meters, plus 20 Newton meters, right? All over 1 over, all over 2 times square root of 2 meters, and that comes from sine 45. So this is 4, sine 45 is square root of 2 over 2, right? 4 meters, square root of 2 over 2. That gives you 2 times square root of 2, which is what I wrote down here. Okay, we put all that together, it gives you 50 Newton meters, over 2 times square root of 2 meters, and that's going to equal the same value that I got earlier, newtons. Exactly the same, right? This thing became this thing. And this one is more explicit because you're considering all of the forces. You have one here, one force here, right? Pulling upwards on the rope. You have one pushing downwards here. You have another one pulling downwards at this angle. You have another one pulling downwards at this angle. So that's the most explicit way to do that problem. Okay, for the next problem, it says find the magnitude of the vertical and horizontal components of the force that the hinge must exert on the rod to keep the system in equilibrium. So now, well, we know what this is. This is 17.67, right? So, similar setup. But this time, we're going to just sum up the components, each x and y components of the total forces in the system. Before, we were considering torques, right? We had a torque here, a torque here, a torque here, and a torque here, because there's a hinge point here, right? So now we want this hinge to exist. We're saying what must this thing be exerting on the rod in order for it to stay in equilibrium. So let's do this. Let's sum up all of our y components again. So now we'll call this hinge FH, right? FH in the y direction plus FTY minus FW1 minus FW2. And this is for the y direction, remember, and we are in equilibrium. So now we have nothing in motion, we'll say. So FH is the force we're looking for in the y direction. Call that y. FTY is going to be 17.67 sine 45. Minus 10 newtons, we know that's the weight force. Minus 10 newtons, we know that's also the weight force, right? These are pulling down here. Equals 0. So anyway, we have 20 newtons minus 17.67 times square root of 2 over 2 newtons. That's going to be our force, and that gives us a value of 7.51 newtons in the y-hat direction. So that's the force exerted by the hinge. Okay, and now for the x-hat direction, we do the same thing. Just sum everything up in the x direction, right? So, well, this is y direction, this one is y direction. The only y direction forces, the only x direction forces we have are from the tension force. So we have a tension in the x direction, and we have a from the hinge pushing outwards, right? So let's do this. F hinge x minus this tension force pushing opposite. This is pushing outwards. This is pushing outwards. This is pushing inwards, right? So minus ftx equals 0. Again, we're in equilibrium. So fhx minus 17.67 newtons sine 45 degrees equals 0. So fhx is equal to 17.67 times square root of 2 over 2. That gives us a value of 12.49 newtons in the x-hat direction. So just taking these explicitly writing out the values here. right? These are the answers. There you go. So those are the components. And that's what you're asked to find. Thanks.